All right, I suppose that we have a quorum, so we can probably get started. Welcome to, I guess this is lecture 6, where we'll be covering the development of the multiwire proportional chamber, which is a critical enabling technology for high energy physics research, still used today in many experiments. And we'll look at some goings on on the discovery side, the so-called November Revolution of 1974, where a couple of new fundamental particles are discovered in quick succession. You'll start to see the evolution of experiments that look a lot more like your modern collider experiments. And that evolution is going to continue through the next several lectures. So we'll start to sort of pick up the thread that gets us to where we are now in terms of experiment design and collider design. So on the instrumentation side, we've spent the last couple lectures looking at a couple of different technologies, each of which were instrumental in making some important discoveries, but which also have some serious drawbacks which experimenters would like to redress. So synchrotrons are pushing forward to higher energies and higher intensities, sort of with each passing year in the 1960s. This enables fixed target experiments that can look for more massive resonances by virtue of the higher energy, but also for rarer processes by virtue of the higher intensities. Bubble chambers, as we saw in the last few lectures, were for a long time, for about 2 decades in the 50s and the 60s, they were the experimental design of choice for a lot of the experiments looking for these new resonances. Just to remind you, one of the virtues of the bubble chamber is that the detector and the target are integrated together. The liquid hydrogen inside the bubble chamber is a convenient target because of the simplicity of the hydrogen nucleus. You can ignore a lot of nuclear physics that's important for larger nuclei, and the fact that it's held under immense pressure makes it much denser than the gas targets which were used in previous experiments. And not only is the liquid hydrogen a decent target, but it's also a good imaging medium for the particles. Remember, what we do is we expand the chamber a few milliseconds before the particles arrive, and this means that the hydrogen liquid is superheated when the interaction happens. This superheated hydrogen wants to boil, but it needs something to nucleate the bubbles, and the ionization of charged particles passing through the liquid provides those nucleation sites for bubbles, and it's the bubbles which we photograph. The density of the track, in terms of the number of bubbles created per unit length, tells us something about the specific ionization of the track and can therefore be used in order to identify the particles. So it's a good technology, but it has some serious limitations, which I think we've already mentioned. The first is the requirement that we expand the trigger before, expand the chamber rather, before the interaction happens means that the rate of these experiments is limited by the time it takes to do that expansion and then repressurize the chamber afterwards. And it prohibits any kind of selective recording or triggered readout. The requirement that we expand and then the interaction happens and then we take the photograph means that we can't use any information from the interaction in order to determine whether or not to capture the event. And as a result, you need lots of infrastructure for analyzing in some cases, millions of photographs that are taken. As long as you're going to expand the thing and record the interaction, you might as well take a picture of it for offline analysis. And we saw in the last lecture the sort of infrastructure that had to be built up, I guess now 2 lectures ago, the infrastructure that had to be built up in order to analyze all these photographs, right? So you had these scanners, typically women working in very large teams with these huge projection systems that enabled them to measure the track parameters and record them in a way that was amenable to computerized analysis. And then there was this whole industry of data sort of reduction in order to allow the person doing the experiment to discover a particle or discover a new resonance. We talked about this Berkeley-itis idea that the person doing the final analysis is several layers of abstraction away from the actual experiment, in some cases to start to lose the feeling of connection to the experiment itself, which is a problem that I think we still deal with in the field. Another problem with the bubble chamber is that the infrastructure, you have heavily pressurized hydrogen gas, so you need strong mechanics to contain this stuff. Hydrogen is extremely flammable, indeed explosive. And there were several high-profile accidents, including ones that had fatalities associated with them. And there's just a very large and difficult task to maintain and operate these bubble chambers. So you would like to have a technology which is a little bit more friendly to the experimentalist. The spark chamber, on the other hand, which is pictured at right here, has some virtues which the bubble chamber doesn't have. The spark chamber is fully electronic. I mean, there's a gas inside, but the readout can be done by means of electronics. We talked about how people use like television cameras to look at the sparks and record the data, or they used microphones to record the little clap of thunder that comes from the sparks. And this enabled you to get the data out of the spark chamber and into your software in a much more direct way without having to worry about analyzing reams of film. The spark chamber is easily paired with an external trigger. We saw the discovery of the muon neutrino, which is a classic example of this kind of spark chamber experiment where you have interleaved panels of plastic scintillator, which are providing a trigger signal based on PMTs reading out the scintillator that can then be paired with the spark chamber in order to create a data acquisition, which looks much more like what we might be used to. On the other hand, the information which is extracted from a spark chamber is less than for a fully imaging system like a bubble chamber. It's very difficult to measure the specific ionization in a spark chamber because you're operating in this mode where the spark is sort of binary, it's there or it's not. So what we would like to do is come up with a fully electronic system which somehow merges the virtues of both of these approaches. A fully electronic system which can have a imaging capability, which is sort of more like a expansion chamber, both in the sense of having a larger spatial, richer images in the spatial and in the time dimension, something that's the time dimension lacking almost entirely from bubble chambers, but whose signals can be processed in a fully electronic way, like the spark chamber, without having to record millions of film images in order to do the analysis. And the technology which is going to fulfill this desire and continues to be an important part of our experiments to this day is called the multiwire proportional chamber. The inventor of the multiwire proportional chamber was this guy, George Charpak. He was born in 1924 in Poland, but now it would be Ukraine, the part of Poland that he was born in. But his family moved to Paris when he was just 7 years old. So he was, in his late teens when World War II broke out. He actually served in the French resistance during the war. And he was captured by the Nazis and interned at the Dachau concentration camp, where fortunately he was not executed before the Allies could liberate the camp in 1945. In the late 40s, the French government wanted to rebuild the successful culture of nuclear and particle physics that they had had before the war. And so there was a major effort to identify talented young people who could contribute to nuclear research. And Charpak was so identified. And in the late 40s, he worked with Frédéric Joliot-Curie on the first French nuclear pile. And he did a number of investigations in nuclear physics with the CNRS, which is a French national research agency, before moving to CERN in 1959. So CERN was still relatively young at this point. In 1959, when he joined the staff of CERN, he was sort of explicitly tasked with developing new detector technologies. And it was during the sort of 10 years following from 1959 to 1968 that he invented and then improved and further developed this multi-wire proportional chamber. This sort of immediately supplanted bubble chambers as soon as the technology could be proven, because it really is the best of both worlds in terms of having a fully electronic triggering or triggerable readout without a lot of the infrastructure that's required to sustain a bubble chamber. And we'll see in a minute some of the complications that do arise in manufacturing a good quality multi-wire proportional chamber, but it's a much simpler and more robust technology than the bubble chamber. He eventually received the Nobel Prize in 1992 for this work primarily, as well as some other contributions to the science of particle detectors. So how does it work? What's the idea here? So the multi-wire proportional chamber is in some ways similar to other gaseous detectors that we talked about a few lectures ago. We talked about when we were introducing the concept of the Geiger-Müller tube, the idea that you can run these gas detectors with a cathode and an anode in different regimes, depending on the voltage you apply and the gas mixture that you have and the amount of ionization that you're expecting the particles to cause as they pass through the gas. You can choose the voltages such that you're in this proportional regime. And recall that when we say proportional regime, the proportionality that we're talking about is the amplified signal that's recorded by the electronics relative to the initial amount of ionization. So the way that this gas amplification occurs, just to remind you, is that we have primary ionization events. Imagine we have like a muon passing through this tube. The tube is filled with gas. The muon occasionally will interact with the gas molecule and produce an electron paired with a positive ion. Here, this picture is drawn for the electrons. There's a sort of similar process that happens with the positive ions, but with some differences in the gas, which we'll address on the following slides. But the basic idea is that you amplify the size of the original ionization event through successive generations of secondary ionizations. And then the amplitude of the current pulse that you measure on your wire is proportional to the energy which was transferred in the original ionization event or events. And this proportionality allows you to recover the information about the specific ionization of the particle, the DEDX of the particle, which was largely missing from electronic detectors up until the invention of the proportional chamber, certainly from spatially segmented detectors. So recalling that, we can look at how multi-wire proportional chambers are typically made. The main insight that Sharpak had that resulted in the design of how these chambers look is the realization that you don't actually need to have a mechanical or electrical separation between the individual anode wires. So you can fill your chamber volume with individual wires as long as they're at a suitable distance from one another. You don't need, for example, ground planes in between in order to contain the field lines. We'll see in a bit a picture of what the field geometry ends up looking like in this kind of arrangement. So you have, in this type of geometry, you have cathodes, which are just conducting planes. They can be segmented, and we'll talk a little bit later about why you might want to segment them. But in this simple example, there's no segmentation of the cathodes. They're just metal sheets. And then in between these sheets, you have the gas. That's where the amplification is going to happen. And then you have the anode wires in the volume parallel to the cathode plates. And the distance between the individual wires is called the pitch, indicated by S on this diagram. So typical values of the sizes of these objects are given on the bottom of the slide here. The diameter of the wires, the radius of the wires is about 0.01 millimeters or 10 microns. So we're talking about quite a thin wire. The typical pitch is about 2 millimeters. That's related to the typical drift in space that the signals are going to undergo. And we'll talk more about that later. As it turns out, you would not gain much from having a much finer pitch of wire because the signals are sort of intrinsically spread through space by the diffusion of ions and electrons in the gas on their way to be measured. And the distance between the wire and the cathode might be something like 8 millimeters. So we're talking in this simple geometry about a relatively thin counter. Thin counters are usually good in the sense that we want to also spatially locate the signal in the sort of Y direction on this plot. And if we have a very thick chamber with only one layer of wires, we lose information about where in the y direction and the vertical direction the particle passed. We'll see a little bit later on how you can build multi-wire proportional chambers with lots of layers of wires in the same volume by converting the cathode from planes into other wires, but we'll come back to that. So in this geometry with the separations that are pictured here, really every one of these wires can be considered as an individual proportional counter tube, even though there's no mechanical separation between them. The signal charge is going to be generated in the vicinity of one or two individual wires. You know, you can imagine the case where a particle is passing through sort of equidistant from these two wires. And then probably you can picture that the charge that's generated is going to be drawn sort of equally onto those two wires, but very little charge in that case is going to land even on the wires which are one wire further away. The signal charge on the wires is going to be mostly generated by the drift of ions in the amplification region. Here, the electric field of the wires which are further away is really small. And so we don't have to worry too much about the sort of crosstalk between the wires, although some amount of signal being spread between adjacent wires is useful for calculating the trajectory of the particle, about which we'll say a little more later. The other advantage of leaving out the any kind of mechanical separation between the individual channels is that you reduce the overall mass of the detector, which is desirable in the case where we want to measure the momentum of particles in like a spectrometer without having too much, multiple scattering, et cetera, in the material, which would worsen the momentum resolution. So this is a great idea because it enables us to fill a large detector volume with a relatively low mass detector with good spatial resolution. As we'll see, it also has pretty good time resolution. And the readout is fully electronic, involving no photographic film or anything like that. The main advantage relative to the spark chamber is a much shorter dead time. So spark chambers utility is really limited by the fact that it takes a long time for the very high voltage of the spark chamber to recover from this massive current pulse before it's sensitive to another particle passing through. By clever choice of the electric field, the gases, and the physical size of the elements, we can reduce by a lot the dead time of a fully electronic detector. And the multi-wire proportional chamber has a much better lifetime than a spark chamber. One of the downsides is that we would like to read out each of these wires individually in order to fully exploit the spatial and time information which is available to us. And that means that we have to have a separate electronics chain basically for each of these wires. So in the old days, when people were working mostly with like vacuum tubes as amplifiers, it's difficult to imagine, the physical size of the amplification device per wire is very large, and it's difficult to imagine how you could manage all those components and all the heat that they generate, et cetera, for large numbers of wires. So this invention of the multi-wire proportional chamber is sort of inextricably linked to the ongoing miniaturization of electronic components, which results also in components which are consuming less power and generating less heat. So even if you had this idea in the 1920s, the electronics simply wouldn't have existed in order to implement it. But by 1970 or so, those electronics are becoming available to physicists. The way that you typically manufacture this chamber is by winding. So imagine a simple geometry like the one we had on the previous slide, where you have one layer of wires, which is spread across a plane sandwiched in between two cathode plates. It turns out that there's a convenient way to manufacture this thing by taking one long wire and winding it around the chamber. So you see here, this guy has a big sort of spindle that he can rotate. There's a chamber on this thing, and then he's able to basically draw a wire off of a spool and wrap it around this chamber by spinning this thing. And he can maintain a constant tension during this operation. We'll talk on the next slide about why keeping the wires under tension is important, by basically having a pulley with a weight suspended from it so that the tension in the wire is maintained at a constant value as this winding process goes on. The wires, as I said, are quite thin. Depending on the material that's used, they might be sort of tens of microns, and therefore the mass which is attached to the wire in order to apply the appropriate tensile stress is actually quite small, given the fact that this wire is so thin. We might only need a weight in the realm of like 20, 50, 60 grams in order to get the appropriate stress. Why do we want the wires under stress? It's because of the electrostatics of the situation. If the wires are too loose and you try to charge them all up to the same voltage, they're going to feel an electrostatic repulsion from one another. And that's going to make, this is harder to do with my fingers than I thought. It's going to make the wires want to move away from each other, move out of plane. And that's down to the repulsive forces between wires, which are held at the same potential. So we need to have this weight on during the wrapping. We need to have this tensile strength applied during the wrapping process in order to keep the wires under enough tension that they don't move out of alignment. Because of course we don't have any way of, once the chamber is finished and installed, we have no way of seeing inside to like redo the alignment of the wires. So we really depend on the mechanical forces to keep the wires aligned in the plane. The combination of the tensile strength of the wire and the tension that you need to keep the wire straight results in a practical upper limit on how long these wires can be. As it turns out, the maximum free length of the wire for the typical wires that are used is a little bit less than a meter, maybe 80 centimeters or so. So that sets the sort of characteristic size of the chamber. You see that probably the chamber that he's wrapping here might be around 80 centimeters in length. There's some mechanical engineering that goes into doing this well. Obviously, if you want to have longer wires than 80 centimeters, you need to have some kind of insulating intermediate supports along the way to hold the wires in place so that they can't move out of plane. And then you also, the frame that goes around this whole thing needs to be strong enough to hold, you have this tension on each wire multiplied by the number of wires can add up to actually a pretty significant force. So you need to have a strong and stable external frame to prevent the chamber from collapsing along the dimension of the wires. I don't think I have it in this talk, but if you go on the Google, you can find pictures of chambers which were insufficiently strong and they end up getting crushed by the force that the wires are applying to the frame. And of course, this frame is also typically going to be part of the pressure vessel, which is holding the gas. So you want to make this frame not only mechanically strong, but also gas tight, but also as low mass as possible, especially if you're going to have multiple layers of these detectors. You would like to make the walls relatively thin so that you limit the amount of dead material, which is going to scatter the particles in between measurements by the plane. So there's a lot of sort of art that goes into making these chambers well. So you then charge up these wires. In the case where they're all anode wires, then you end up with a electric field which looks something like the picture here. So you have these potential lines which are sort of concentrically around the wires, and then you have the field lines at right angles to the potential lines, which show the direction of the electric field, and that's the direction that the charged particles produced by ionization of your particles going through the gas are going to tend to travel along these field lines. Remember from the first lecture that we're able to analyze the amount of ionization that a particle is expected to produce. The dEdx of a particle in terms of the speed of the particle in the medium compared to the speed of light, as well as the properties of the material that it's interacting with, the Z and the A of the material, as well as some constants related to electromagnetism. For gases that are interesting to use in multi-wire proportional chambers at pressures close to atmospheric pressure, so we're not talking about super overpressurized things like the bubble chamber, but things which are relatively close to atmospheric pressure, the DEDX in kilo-electron volts per centimeter, which you can see in this column of the table here, is typically in the range of like 1 to 10 keV per centimeter. So you can start to get an idea of how much energy, for very high energy particles of like GeV, this is totally insignificant. But if you're doing, nuclear physics with one of these counters, that may be a significant fraction of the incident particle energy. One thing that I think is interesting is that when you think about these ionization processes, I at least don't have a good intuition from first principles of like how many ions per centimeter are actually produced by a relativistic particle traversing the gas. And you see that it's actually a rather small number. So this NP column here is the number of discrete ion pairs produced by the primary interactions. So that's before we take into account the further interaction of the charged particles with the gas after the primary ionization occurs. And it's interesting to note that these are typically small numbers on the order of 1 to a few dozen primary ionizations per centimeter. If the primary ionization event is significantly energetic, or I should say sufficiently energetic, then the liberated electrons can themselves leave a trail of ionization, which you may recall we know as delta rays. If you remember back to the nuclear emulsion and chamber photographs that we saw in the first couple of lectures, you would sometimes have this little kind of hair sticking off the sides of the tracks in those photos. The same thing happens in a multi-wire proportional chamber. And that's why the total number of ion pairs generated per centimeter, the last column of this table, is rather higher than the primary. That's because we can have delta rays of sufficient energy that they actually themselves have several primary or let's say secondary ionization events before the particles start getting accelerated by the applied field and enter the amplification stage. So the number of ion pairs created by these delta rays can actually be as much or more than the primary particle. Let's look, for example, at this line for oxygen gas, where only 22 ionization pairs per centimeter are created in the primary interaction, but the total number of ionization pairs per centimeter is actually 73. So that's more than a factor 3 more, meaning that delta rays, the physics of the delta rays interacting with the material are very important to the total amount of charge that you observe. You can't just use this NP column because you'll get the wrong size signals for your chamber. Since these n's are small, in the range of a few to a few dozen to a few hundred, the statistical nature of the energy loss in gas is important. And there's a picture kind of further motivating that on slide 9. Because the number of individual interactions are small, there are large fluctuations event to event or particle to particle in what the height of the pulse that you would expect to see in your proportional counter actually is. Or said another way, the energy loss in a given gas volume from particles of the same species and energy is rather broad. So this has a couple of practical consequences for people who are designing these chambers. The first is thinking about the electronics chain that you want to attach to your wires. So for a single channel, the dynamic range that the electronics has to absorb is significant. There's a factor of 10 or 100 between the lowest energy signals, which you might frequently see, and the highest energy signals that you might see. And this also has implications for the efficiency of a thin detector. If we're trying to detect particles while absolutely minimizing the amount of scattering off the material, for example, I might be driven down to extremely thin chambers on the order of 1 millimeter thick. But if I do that, there's actually a significant probability that no primary ionization events will occur in that thickness of 1 centimeter. Going back to the previous page, for example, if we were to choose argon gas, which has typically 30 ionization pairs per centimeter, now I go down to a thickness of 1 millimeter. That means I have only 3 primary ionization events per millimeter. And statistically, that can sometimes result in 0 primary ionization events. And so there's a trade-off between the amount of material in the detector, the thickness of the detector, and my efficiency to observe a hit at all. In fact, some of the measurements of gas properties, which you see in these tables, are based on this effect. People build proportional chambers which are as thin as possible, and then they can compare the intensity of the source measured in another way to the number of signals that they see in the ionization chamber and confirm the efficiency measurements that you would get from this simple combinatorics exercise here. The second reason why this effect is practically important to a chamber builder is that most of the time, or much of the time, we want to measure the DEDX. So the problem is actually more complicated than just seeing any signal at all or any signal above threshold. We would also like to be able to resolve, for example, the energy lost by a proton passing through the chamber from the energy lost by an electron passing through the chamber. That's a relevant distinction that a lot of experiments would want to make. That means that a single measurement by a few millimeter thick chamber is not going to be sufficient to make a DEDX measurement, because you see that we can measure, 50 units of charge from one event, 10 units of charge from the next event, but those are from the same initial particle species and energy of the initial particle. So that means that tens or even hundreds of independent measurements are needed if I want to reliably measure the DEDX with a good resolution. Both of these effects are going to be mitigated if I have a thicker detector with more electrodes, and that's why chambers are pushed to a geometry which has multiple layers of wires, as we'll see a little bit later on. Another interesting physics that's going on inside of these gas detectors is the impact of the statistical nature of the process on the time resolution of the detector. So this is a plot which shows for a number 34 ion pairs per centimeter, which I think is chosen because it's typical for argon, which, as we'll see, is an important gas for making these chambers. Even if I send the same track on the same trajectory, so imagine I have a collimated source of protons going through my chamber. So all the protons are going through on the same trajectory, and that means that they're the same distance away. If I measure the distance between that track and the point of closest approach on that track to the nearest wire, even if that's always the same, the statistical nature of the process means that the actual location of the nearest primary ionization event to the wire is not always going to be the same, even if the trajectory of the particles is. And that puts an upper limit on how good the time resolution of the chamber can be. So typical drift velocities in these chambers are going to be measured in like centimeters per microsecond. And so that means a difference between 1/2 and 1.5 millimeters is going to be significant in terms of the timing of the signal, even if everything about the incident particle is the same. Even in the case where I had no external field applied, so let's imagine that I have just a very low voltage between the anode and the cathode, such that the ions and electrons are not going to undergo any kind of acceleration, any significant acceleration before they're collected. I will still observe some kind of spatial broadening of the signal, and that's due to the diffusion of the ions and the electrons through the gas, just due to their intrinsic energy, right? So when I have these ionization processes happening, I'm producing like a cloud of charged particles. Each of those particles has its own energy. There's the intrinsic temperature of the gas, which gives all of the gas atoms and molecules some initial velocity, a distribution of initial velocities, which is temperature dependent. And then I give them some additional energy through the scattering of the of the particles I want to measure off the gas molecules. And that means that these particles are going to have some velocity in most cases, which is perpendicular to the movement of the ions and the electrons through the gas. And that will lead to sort of an unrecoverable broadening of the signals by the time I have a chance to measure them. So we're talking about chambers, which might have separations between the wires or separation between the anodes and the cathodes of like a few millimeters. And you can see that over time, even at 100 microseconds after the initial interaction, I might have moved just due to the motion, the energy of the gas molecules, a significant fraction of a centimeter through diffusion. Both types of charges are going to move through the gas by diffusion, and as they diffuse through the gas, they have encounters with other gas molecules which may not have been ionized by the initial ionization event. Eventually, in these interactions, a recombination will happen, either at the walls of the chamber, which are conductors, so there's just free charges available to recombine there, or sometimes within the gas, especially if I choose a gas which is highly electronegative, so something that contains molecules like chlorine or fluorine, which have a big appetite to absorb electrons. The recombination probability, even before reaching the chamber wall, might be high. Noble gases, on the other hand, like argon, which is a favorite of chamber builders, they have almost zero probability to absorb ionization electrons. And therefore, the signal that I receive at the wire is going to be higher for a gas like argon than it is like freon, for example. As it turns out, I want to have a mixture of both types of gases because I want my initial signal to be large, but I also want it to be quenched by electronegative atoms so that electrons and ions don't travel too far before recombination happens. So a noble gas will provide a large initial signal, but a very low recombination probability. That means that the signal can spread widely through space. Whereas an electronegative gas, the signal reaching the electrodes will tend to be smaller because many of the electrons get gobbled up by the gas molecules before they can be read out. But they have the positive consequence of keeping the amplification to a more compact spatial region. And it turns out that what we want is a combination of those two effects. Once I introduce a strong external field, which is usually going to be the case here, I'm going to be holding the anode and cathode apart in voltage by some high voltage order of hundreds of volts, depending on the application and the geometry of the situation. In an external field, the behavior of ions and electrons in the gas is actually quite different. So starting from the case of the positive ions. So positive ions of the gas are heavy. They have a nucleus, which is much heavier than the electrons, of course. And so they do not manage to accelerate much in between interactions with other gas molecules. So they very quickly reach like a terminal velocity as they're propagating through the gas based on the sort of short mean free path in between the interactions combined with the mass of the particle itself. And this leads them to basically more or less immediately reach a constant average velocity, which we call the drift velocity. Here it's annotated as W, the drift velocity W. For positive ions, the drift velocity turns out to be linear proportional to what we call the reduced electric field. That's E over P, the electric field strength E divided by the pressure of the gas. It's this ratio which determines basically how much energy the individual ions are picking up in between each of their interactions with other gas molecules, and therefore is related to the final speed that they attain in drifting through. So we define this quantity called the mobility, which is written here as mu. The mobility basically tells us what the ratio of the drift velocity to the electric field is. And that allows us to easily compute the drift velocity for positive ions in the gas under a given pressure and electric field. So you can see here this mobility. So it's divided by the pressure, which is where this centimeters squared comes from, and then inversely proportional to the electric field strength, which is where this volts to the -1 comes from. And then it's a speed in like centimeters per second, which is where this per second comes from. And this is going to be in the range of like 0.3 to 3 or something like that. For mixtures of gases, it's a good approximation that the mobility can just be summed as the partial pressures of the individual gases. So you see the simple equation for summing together the individual mobilities here, using the partial pressures of the different gases in the mixture. And then you can see in this plot, figure 21, there's inverse mobility plotted for a number of different mixtures of argon and methyl gas, which is a hydrocarbon gas. And you can see that the points which are experimentally measured follow well the curves predicted by this simple sum rule. So that's a nice feature. If we have some new gas mixture that we want to try out, we can pretty reliably calculate what drift velocity we expect the ions to attain, as just knowing the mobility in the individual component gases. For electrons, the situation is rather different and rather more complex. And there's two main reasons for that. The first reason is that electrons are much lighter than the ions, of course. And so unlike the ions, electrons actually accelerate a lot in between their collisions with individual gas molecules. So there's not as easily a single drift velocity that they immediately maintain. And we have to think of the electrons in terms of a distribution of energies or a distribution of velocities, which sort of makes everything more complicated. So at every stage of the amplification process, we have a population of electrons with a spread of energies. And this is made more complicated by the fact that EV scale electrons, which is a typical energy that these things maintain. So here we have a 760 volt per centimeter chamber at atmospheric pressure. Remember, I said that typically we're talking about hundreds or thousands of volts of high voltage on these chambers, and typical sizes of like millimeter to centimeters. You can see that there's a spread of energies between, say, 0 and 5 or 10 or 20 electron volts, depending exactly on how strong the field I apply is. Obviously, all else being equal, the stronger the field, the broader this distribution will become and the higher the peak energies. Then you combine that with this figure 24 on the bottom, which is showing the cross-section for electrons to interact with the atoms in the gas as a function of their energy. This is for argon, but you could draw similar things for all different gases, and they would all be different depending on the electronic structure of the gases. Because this EV energy scale is similar to the binding energy of the outermost shell of electrons in most atoms and molecules. That means that the interaction probability is going to evolve, sometimes in quite complex ways, with multiple local minima and maxima within this energy range of like 0 to 10 EV. I see a big change in the interaction cross-section. So you have to pair this probability to find electrons at these different energies with this varying cross-section as a function of energy, and the result is a sort of complex behavior which doesn't follow the really simple laws that the positive ions do. As a result, the drift velocities for electrons in the material are not just a simple function of electric field. They don't just increase linearly with the reduced electric field as they did for the positive ions. And the addition of even small concentrations of gas molecules with a different interaction cross-section can actually have dramatic effects on the typical drift velocity of the electrons in the material. So you see here that adding just a 1% nitrogen to our argon will increase the drift velocity that I observe, typical drift velocity that I observe, by a factor of 5, even though the admixture is only 1%. So that's a little bit counterintuitive. And here you see for a mixture which is especially dear to MWPC builders, argon isobutane mixtures, that this drift velocity as a function of the field has a complex shape, which isn't as easily parameterizable as it is for as it is for the positive ions. So again, you see individual local maxima and minima in some of these curves, and the location of those things is varying significantly based on the fraction of isobutane that we introduce. So it's complicated. Finally, just like the positive ions, the electrons are also diffusing through the gas as they're drifting, and this will again place a limitation on the spatial accuracy that I can attain. So you see here for a gas like argon, which is good because it gives a large primary ionization signal without much recombination. There's also a lot of drift that happens before they reach the electrode. This is the sigma of the transverse size of the electron cloud after 1 centimeter of drift. And you see that it's actually a significant fraction of the drift for argon. For a 1 centimeter drift and a typical operating voltage of 500 volts per centimeter, we're up close to 0.2 centimeters of transverse drift for every 1 centimeter that they propagate through the gas. And so this is obviously not the greatest thing if we want to have a good spatial resolution on our detector. We can improve the situation by adding one of these other gases like isobutane, where the initial signal will be smaller, but so too is it going to more readily absorb electrons as they're wandering through the material, and therefore we get an attenuated but more spatially localized distribution of drift electrons from this kind of a mixture. Both the drift and the diffusion are affected by the magnitude of the electric field. And we haven't yet talked about the fact that we're also typically going to be putting these things into a magnetic field, because we might want to build a spectrometer that's measuring individual particle momenta. And as you can imagine, having these sort of EV scale electrons and then immersing it in a strong magnetic field, say 10 kilogauss, will affect a lot what the typical drift velocity is. And this is also dependent on the angle between the electron and the magnetic field, right? Because the Lorentz force is depending on the cross product of the magnetic field and the electron velocity. So this is another aspect in which the electrons in particular in these detectors, the physics of what they do is quite complicated. To that, we can add a whole laundry list of other things that we might want to have our chamber, ways that we might want our chamber to behave. We would like to have a high ionization density. So this drives our choice of the main component of the gas mixture. We want to have something which is dense enough in terms of typical number of ionizations per unit length that I don't have to build a really long chamber with huge separations between the wires, because that would denigrate the other or degrade the other performance. The spatial and time resolution of a very large chamber with very large separations would be very poor. So we'd like to avoid doing that. We don't want to lose too much of the charge as things propagate through. If we use like pure isobutane or something that had, or even worse, pure freon, which would have a very large chance for recombination, we might not see much of a signal actually reaching our anode because it all gets resorbed on the way through. We would, all else being equal, prefer to work with lower voltages rather than higher ones for safety reasons, among others. And so we would like to, we want to be in the proportional regime, but we would like to do that with as low of a applied voltage as possible. We would like it to operate stably. In particular, we would like to have the characteristics of the gas such that an actual spark, like we see in a spark chamber or a Geiger tube working in the Geiger mode, we don't have those sparks, because when we have a spark, that means that the takes a while for the gas to remix and recover so that we'd be sensitive to another particle going through. We would like to stay in the proportional regime. We would like to limit the transverse diffusion, especially as much as possible, to improve the position resolution of the detector. And we would like the drift velocity to be suitable relative to the physical size of the detector and the expected event rate, et cetera, in order to maintain that position resolution. We'd like to be able to tolerate the appropriate rate with low or no dead time. which means that we would want a low charge accumulation in the space of the detector on the time scales, which are typical event to event. It might need to be radiation hard if it's going near a high intensity source, either a beam or a radioactive source. And we would, all else being equal, prefer to have safe gases. That means not flammable, not toxic, and environmentally acceptable. So I talked a couple times about using a gas like Freon for its highly electronegative fluorine atoms, but we now know that Freon is bad for the ozone layer, so we probably don't want to be blowing a lot of Freon off into the atmosphere if we can avoid it. And of course, we would like to do this all at low cost. So for many decades, people have investigated different gas mixtures to try to hit as many of these criteria as possible. And one good answer turns out to be something called the magic gas. It sounds like something they would pass around at a party. But what the magic gas consists of is 75% argon. Argon chosen for its large primary ionization signal. It also has good chemical properties. It's a noble gas, so it's non-reactive. So you don't have to worry about it rusting your wires or depositing polymers on the walls of your chamber or whatever. 24% isobutane. This has a high resorption of the electrons which are produced, and in this mixture it quenches the signals and prevents them from spreading out too much in space and time. And that effect can be further augmented by adding a very small concentration, like 0.5% of Freon, which has some highly electronegative atoms inside and aids in an even faster decay of the signal, which helps with dead time as well as improving the time resolution. Of course, Freon, as I mentioned on the last slide, is not very green due to its effects on the ozone layer. And so experiments over time are converting to more sustainable gas mixtures, which, however, might have other undesirable properties. So having built my chamber, filled it with the appropriate gas at the appropriate pressure, and having determined my operating voltage that's suitable for the size of the chamber, the energy of the particles that I expect to measure, and the geometry of the situation, I can then attach each of my wires to individual readout channels. So if I have a charged particle going through my chamber, what I will see is a large current pulse on the wire which is closest to the signal, a somewhat smaller current pulse maybe on the wire which is second closest. The ratio of these pulse heights is related to the distance in between the wires. So I have a spatial resolution, which is actually a bit better than the pitch of the wires. I can see that this wire signal is higher than this one, and so I can weight the best guess for where the particle passed through to be closer to the wire with the higher signal. And then if I look at a wire which is further away, I don't see anything at all because I'm only going to see a signal on the 2 or 3 wires which are closest to the initial particle trajectory. So I don't want the signal to be quenched so quickly that I don't see any signal on the second wire, because that would actually degrade my position resolution. I would no longer be sensitive to where in the volume between these wires my particle went through. I can then further improve this by adding additional planes to my detector. Typical strategy might be to put the planes staggered, rotated, or offset in some way, such that I have actually independent measurements in different axes. In this picture, they're all aligned, but with some kind of spatial stagger. And you can see, I think, from this example that I can first localize on each of these planes where exactly the particle went through. And then knowing the location of each plane, I can then figure out what the sort of 2 or 3-dimensional trajectory of the particle was, knowing the separation between the planes and the coordinate on each plane. I can do even better by combining planes which are rotated with respect to one another. In this picture, I have 2 examples, one where I have 2 layers where the planes are rotated by 90 degrees. Then if I read out my signal in time, I will have one set of wires which is firing here, and another set of wires which is firing here. And I can try to reconstruct the 3-dimensional trajectory of the particle by stacking up multiple layers of these crossing planes And with each individual layer that I add, I reduce the number of spurious combinations, and only the true combinations where the particle actually went through will survive on multiple independent layers. Some experiments also use even more complex geometries where I rotate, add a third plane to the first two, and then I can have different rotation angles between them depending on the occupancy that I expect in my detector versus the separation of the wires and the thickness of the planes, et cetera, determines what the best way of doing this is. And then, of course, some of this work is going to be done by software off detector. So I'm also thinking in terms of, I may not need to fully solve this ambiguity about which combination of wires is the true hit position, maybe until later in offline analysis. It all depends what my chamber is being used for. So summing that all together, we end up with detectors that look like this. This is the Babar central drift chamber tracker with sort of all of the external pressure vessel and everything taken away so you can look at the wires directly. It's kind of a low resolution photo and then probably further smeared by being transmitted by zoom, but perhaps you're able to see these kind of places where the light is glinting off the wires, and it's sort of in vertical lines where the light is glinting off the wires. That's because this is a stereo chamber with a small angle between. There's like two sets of wires in there with a small stereo angle in between. So these locations where you're seeing the sort of banding between the wires here, which I think you can maybe see well in the area where there's these reflections or whatever, that's due to the stereo angle between bunches of wires. So sometimes in space they're close together and you see a higher density, and sometimes they're further away because of that angle between the two sets of wires. And so you can imagine then what the offline software needs to do is to look along a region of space that you think the track passed through, and by looking at where the two wires that have a crossing angle between them, where those wires both fire in coincidence, will give you candidates for where along the track, where along the Z direction the track went. And then by having multiple layers of that, you can eventually solve all the ambiguity away and calculate where the real tracks went through. A second thing that you may want to do is to actually segment the cathode. So far, our sort of chamber that we had in our head was two just cathode planes with the wires running in between. One thing you can do is separate the cathode either into strips, which are running perpendicular to the anode wires, in which case you get this sort of two dimensions without having to have two sets of wires, but rather just by segmenting the cathode. Or you can go even further and segment the cathode into pads. So it's hard to read out the locations along the wire individually because the wire has to be strung through space. But the cathode maybe is sitting on top of a printed circuit board or something where it's relatively straightforward to segment it into pads. And then you can get a lot more spatial information out of a single layer by segmenting the cathode. Another thing that you can do is instead of having cathode planes, you can have a second set of wires, which are the cathode wires. And then those can either be in a stereo configuration alongside the anode wires, or they can be in planes which are offset. There's lots of different geometries you can imagine, different cells that you can build up of anode and cathode elements in order to come up with the geometry which is the most suitable for your use case. So this is a flexible and powerful technology, which is used, as I said, still in many modern experiments, not just in particle physics, but also in nuclear physics, in astrophysics, and the like. So this is a great invention, and it enables a new generation of detectors, which are going to make some really significant discoveries. I stopped here last time with a summary of what the standard model looks like around 1974. Electrons and muons have both been discovered. They're believed to be point particles. We now understand that baryons and mesons are composite particles. They're composites of three quarks, the up, down, and strange quarks. And the quantum numbers and the masses of the bound states are related to the quantum numbers and masses of the constituent quarks. We have this simple model of what will eventually be called QCD, where there's 3 different color charges that the quarks can carry, and that determines the pairings which are allowed versus disallowed in terms of number of quarks to make up a bound state. Baryons have 3 quarks, mesons have 2 quarks. We now think that we may have discovered states with 4 or 5 quarks, but that wasn't known at the time. And the quark model was successfully used to predict the existence and even suggest the masses of new hadrons. For example, the omega minus, which is the strangeness -3, strange baryon. We have a theory of the weak interaction. We think that the weak interaction is allowed to change strangeness by 1 unit. This is responsible for the slow decays of the strange particles like the kaon. And there have been a series of experiments looking at parity conservation in weak decays, which have revealed that parity is not conserved in weak decays. That comes from experiments with cobalt nuclei as well as with the neutral kaon system. And this picture is about to be seriously changed in late 1974. So in November of 1974, Burton Richter and his team at SLAC and Samuel Ting and his team at Brookhaven were doing 2 very different experiments. One was studying E plus, E minus annihilation. That's the team at SLAC. And the team at Brookhaven was studying E plus, E minus pairs produced in proton beryllium collisions. What's going to happen very shortly is that they're going to more or less simultaneously discover a new resonance with a mass of 3.1 GeV. And this discovery so profoundly affects particle physics that this period is often referred to now as the November Revolution. Word of these discoveries spread through the high energy physics community very rapidly, even with the sort of primitive communication technologies available at the time. And soon much of the research happening at all the different laboratories was directed towards those new particles. So let's look at the 2 different experiments, one sort of a reflection of the past and one in anticipation of the future. So the process that people were starting to study, among others, was this one. If I have an electron-positron pair and I bring them into contact with one another, they can annihilate to produce a virtual photon, but both energy and momentum conservation cannot be had with a 2-to-1 interaction like that. So the photon has to go back to a pair of new particles. This could be another electron-positron pair, but it can also be something else. In particular, it can be a quark-antiquark pair. And then these quarks, remember, we had hypothesized that the quarks cannot be free. And so they have to hadronize into mesons, usually, or sometimes baryons. And it's that which the experiment would see. So the signature we're looking at is no hadrons in the initial state, for example, by having a beam of electrons and a beam of positrons colliding with one another. And then we want to measure the rate at which we can produce hadrons in these collisions when there were no hadrons in the initial state. And the amplitude of this process is going to be proportional to the number of different ways that we can write this diagram. In other words, it's going to be proportional to the number of different quark flavors that can participate, as well as the different charges and colors that the individual quarks can have. So the rate of this process relative to the rate of another process which doesn't have any QCD in it, like E plus E minus to mu plus mu minus, is predicted to be 2. And so people go and start to do experiments like this to see, is the ratio of hadron production to muon production really 2, or is it something else? The experiment which looks more like the past is this experiment which Sam Ting and company were doing at Brookhaven. So they're looking at the rate of production of E plus E minus pairs in collisions of protons on a beryllium target. So if you will, this is kind of the inverse diagram of the one that we showed on the previous slide. And then they have spectrometer arms which can be moved around the interaction point and measure the invariant mass of the E plus E minus pair. So they can move this arm to different angles. The arm is sensitive to what the momentum of the electrons coming out is, and the combination of the angle and momentum will tell you about the invariant mass of the pair that was produced. if you remember from the previous lecture, we talked about Lederman's experiment at Brookhaven, which was looking at muons coming out of an interaction like this. The electron pair and muon pair approaches to doing this experiment both have their advantages and disadvantages. So the advantage to muons is that they're more penetrating than hadrons or electrons. And so muon pairs can be studied pretty easily by just placing an absorber behind the interaction region. If you have a sufficient thickness of absorber, then it's relatively straightforward to screen out basically all of the particles besides muons. And then you put your spectrometer behind that absorber, and you can pretty easily measure the invariant mass of all the muon pairs that are being produced that way. That allows you to do experiments with very intense beams, because even if the lifetime of your detectors is not that good, or the time resolution of your detectors is not that good, the absorber does most of the work for you in screening out the debris of almost all of the collisions, and only the muons get through. However, the muons are subject to multiple scattering in all of this absorber material, and that places an upper limit on the momentum resolution that my counters behind the absorber can have. So the idea of Ting's group was to do electrons instead of muons. There, you don't have the advantage of all this absorber to screen things out. So you need a particle ID system. He used multiple different Cherenkov counters to screen out things like pions and kaons and identify only the electrons. But those things are much less massive than the material you would need to build a dedicated muon system. And as a result, the energy resolution, or the resolution on the invariant mass that Ting is able to achieve here, is much greater than Lederman's group working on muons. So they're going along doing this experiment, looking at different center of mass energies by the energy of the beam, which is coming out of the accelerator. They see a little bit of a shoulder in their invariant mass distribution around 3 to 4 GeV, but the Lederman group had seen this shoulder, but was unable to resolve it. But the Ting group is able to see it. So the counting rate that Ting had, combined with the resolution, was able to explore the details of this region between 3 and 4 GeV that the Lederman group was not able to see. This experimental setup looks very much like the Pi0 discovery, which we briefly looked at a few lectures ago. This idea of movable spectrometer arms was kind of the way that people were used to doing fixed target experiments. You know, if you went to one of these labs at the time that people were doing experiments like this, you would find that different solid angle was assigned to different experimental groups. So at the same time, Ting is moving his spectrometer around in some angular range, there might be another group working on the other side of the same beamline with their own spectrometer measuring maybe some other species of particle or something like that. This is in contrast to what we do now, which is to surround the whole interaction region with one experiment that allows us to make a much more detailed picture of the collision. And it's around this time that people are going to start to have the idea to do that too, at a new collider, which is being developed in the parking lot, actually, at SLAC. So remember, in the previous lecture, we were talking about deep inelastic scattering. We talked about the electron beamline that could produce multi-GeV electrons at SLAC. And Burton Richter, who was a scientist there, had the idea that they could take some of the beam out of this linear accelerator and put it into a storage ring. And so they put steering magnets around the parking lot here, and they put an electron beam into one side of this thing, and then they had a target which produced a spray of particles when the electrons are fired onto it, from which the positrons in a specific momentum range were siphoned off by means of a suitable magnetic field. And then into the other direction, circulating around this ring, they injected those positrons. And they were then able to bring them into collision at a location here inside of this sort of Quonset hut type building that you see here. So this machine is able to explore the energy range from about 2.5 to about 7.5 GeV. of center of mass energy. This is not the very first collider. There had been lower energy machines of this type, including one in Russia, one in France, one at Frascati in Italy, and the Cambridge Electron Accelerator in Massachusetts. But this is going to turn out to be a suitable energy and suitable particle type to make some really significant discoveries. To exploit this new ring, they also built a detector. This was a joint venture of SLAC and the Berkeley lab, which is just across the bay. And their idea was to build probably the first multi-purpose large solid angle magnetic detector, which they called the Mark I. So in the center of this, there was a cylindrical spark chamber inside of a solenoidal magnet. The spark chamber was the tracking system. This was then surrounded by a series of time of flight counters that could be used for particle velocity measurements, and that could be then folded into a particle identification system in concert with the momentum measurement from the central spark chamber. Then there were shower counters surrounding that, which were used to identify photons and electrons, basically through tagging the electromagnetic showers that they made going through these shower counters. And then there are wire chambers of the design that we just discussed at the beginning of the lecture surrounding that, behind an absorber, and those are used for muon identification. So this thing looks a lot like CMS, for example. And it turns out that this is a really smart geometry for a detector, so much so that pretty much all the collider detectors after this are going to mimic this strategy to some extent. Their idea is to use this detector to study E plus E minus collisions across this energy range between 2.5 and 7.5 GeV that the accelerator is capable of providing. So basically, they're going to measure this ratio that we saw on slide 26. They're going to measure the number of hadron events that they see coming out of these E plus E minus collisions and see if the ratio of hadron to muon events is indeed 2 or something else. So this BNL experiment using the spectrometer arms of Ting and company and the Mark I experiment in Stanford, Richter and company report their results around the same time. So starting with the results from the Brookhaven experiment at left, you see that there is a huge excess of events around 3.1 GeV seen in the BNL detector. Originally, the Mark I detector was not really sensitive to this peak because they had been scanning their energy range in steps of 0.2 GeV or 200 MeV, and they skipped right from the point at 3.0 to the point at 3.2, and that almost meant that they entirely missed this giant structure in between. But they did see an enhancement of the rate at 3.2, which wasn't present at 3.0. That is, this ratio 2 jumped up to 2 point something when you went above 3, and that sort of encouraged them to further investigate this region. So they redid the experiment, but now moving by smaller steps in the range of 3.1 to 3.3 GeV. So basically doing a finer grain scan of the area just around where Ting was seeing his resonance at Brookhaven. And lo and behold, they see the exact same structure. So in proton on beryllium to E plus E minus pairs, you see this massive enhancement of the rate at a center of mass energy around 3.1 GeV. And in the opposite direction, E plus E minus pairs going to hadrons, you see also a massive enhancement of the rate around 3.1 GeV. So this is strong, indeed, sort of earth-shattering evidence for the existence of a new resonance at about 3.1 GeV, and the fact that this resonance changes in a way that persists even as you move above the resonance, the cross-section of E plus E minus to hadrons is strong evidence that there is a new resonance here, which is a bound state of a new species of quark. The reason why the cross section is like durably higher at higher energies than this is that now with 4 quark species, this ratio of hadrons to muons is sort of permanently higher above 3.1 GeV, even when you're off resonance. Frascati, the Italian electron-positron collider, was only designed to go up to 3 GeV. So in principle could not investigate this resonance, but seeing these dramatic results, they pushed the energy of their machine up to 3.1, 3.2 GeV, and they also saw the same thing. So these 3 groups, Brookhaven, Slack, and Frascati, all appeared in the same issue of Physical Review Letters. And the conclusion from the community was a rapid agreement that there's a new species of quark, which we'll come to know as the charm quark, which is turns on at about 3.1 GeV center of mass energy. So if there's a new bound state, there could be other new bound states even higher in energy. For example, an excited state of the same resonance, or a combination of these charm quarks with other heavier objects. And so they start stepping up the energy of the machine even higher to search for other narrow states. So the SLAC LBL Mark I team worked with the accelerator physicists at Stanford to start stepping up the energy of the machine by 1 MeV every minute. And after 10 days of doing this, they discovered another narrow resonance between 3.69 and 3.7 GeV center of mass energy. They continued this search all the way up to 7.4 GeV, but there were no more comparable resonances, at least not of this high amplitude, all the way up to the maximum spear energy of 7.4 GeV. We'll come back to this business of searching for higher energy resonances in the next few lectures, because it turns out that they were just short of what they would have needed to make yet another big discovery. The discovery of this, what will eventually be called the Psi 3096 and the Psi 3685, which is the one pictured here, was a period of sort of intense spectroscopic work on bound states involving charm quarks, which continued for many decades after the discovery. There's a lot of physics that you can study in these resonances that gives you some insight into the quantum numbers of these different states, whether or not they're excited states of the ground resonance or new pairings, et cetera, et cetera. So this really opened up a new era of physics with a new spectroscopy of these charm states to explore. The story is not over. It turns out that there's yet one more thing that you can see at this collider, which was also not anticipated, and I will just end the lecture with a quick tease of that. There were also a few events in the SLAC LBL group analysis which looked strange. There's a few strange things about this event. One of these tracks has hits in the muon system, whereas one has a hit in the shower counter. So this is identified as an electron. This is identified as a muon. So remember, the things that we were mostly studying were like E plus E minus resonances or mu plus mu minus resonances. Well, it's not predicted that there should be a excess of events with an electron and a muon originating from a common vertex. The second puzzle is that both of these particles have momentum towards the left-hand side of the picture here, and there doesn't appear to be anything balancing it on the other side of the picture. So out of 35,000 events that passed the initial selection here, there were 24 such events where they had an electron and a muon, which is not expected. And even more strangely, these electrons and muons seem to be paired with something invisible, perhaps one or more neutrinos, and no additional hadrons or photons. Does anyone have an idea of what this event could be? Well, if not, I encourage you to think about it between now and the next lecture, and we will kick off the next lecture on the further rise of collider physics and the accompanying developments in detectors by analyzing these events and figuring out what they suggest. Are there any questions before we end for today? All right. If not, thanks everyone, and I will see you next time. Bye-bye.
Yeah.
Thanks, bye.